Welcome to our deep dive into the fascinating world of radio transmitters and receivers. In this video, we'll explore the essential building blocks that make radio communication possible. From the basics of AM and FM transmitters to the advanced workings of superheterodyne receivers, you'll gain a comprehensive understanding of how these systems operate. Whether you're a student, hobbyist, or just curious about how your favorite radio station reaches your ears, this journey will clarify the technology behind the magic. Let's start by understanding what radio transmitters and receivers are and why they are so crucial in our daily lives. Radio transmitter is a device that generates and sends out radio frequency signals. These signals carry information such as music or voice over the airwaves to be received by radios. The transmitter takes an audio signal, combines it with a radio frequency carrier, and amplifies it for broadcast. This process is fundamental to all wireless communication, from simple walkie-talkies to complex broadcasting stations. Understanding transmitters is the first step in grasping how radio communication works, setting the stage for our exploration of different transmitter types. AM or amplitude modulation, radio transmitters are among the oldest and most widely used types of transmitters. They work by varying the amplitude of the carrier wave in accordance with the audio signal. AM transmitters are known for their simplicity and long-range capabilities, making them ideal for talk radio and news broadcasts. In this section, we'll look at the two main types of AM transmitters, low-level and high-level. Each has its own unique design and application, which we'll explore in detail. Low-level AM transmitters modulate the audio signal at a low power stage before amplification. This means the audio and carrier are combined at a lower energy level, and then the resulting signal is amplified to the desired transmission power. This approach is efficient for small-scale broadcasting and is often used in local radio stations or educational setups. The main advantage is that it allows for easier control of the modulation process, but it may not be suitable for very high-power applications. High-level AM transmitters, on the other hand, perform modulation at the final power amplification stage. Here, the audio signal is combined with the carrier after the carrier has already been amplified to a high power level. This method is preferred for large-scale broadcasting, such as national radio stations, because it can handle much higher transmission powers. However, it requires more robust and expensive equipment to manage the high energy involved in the process. Pairing low-level and high-level AM transmitters, the main differences lie in where the modulation occurs and the scale of their applications. Low-level transmitters are more energy efficient and easier to manage for small broadcasts, while high-level transmitters are necessary for reaching larger audiences over greater distances. Understanding these differences helps in choosing the right transmitter for specific broadcasting needs. FM or frequency modulation, radio transmitters represent a significant advancement over AM technology. FM transmitters work by varying the frequency of the carrier wave according to the audio signal rather than the amplitude. This method provides better sound quality and resistance to noise, making FM ideal for music and high-fidelity broadcasts. There are two main types of FM transmitters, direct and indirect. Let's explore how each operates. Direct FM transmitters generate frequency modulation directly at the oscillator stage. The audio signal is applied to the oscillator, causing its frequency to vary in real time. This approach is straightforward and effective for many FM broadcasting applications, especially where simplicity and reliability are important. Direct FM transmitters are commonly used in commercial radio stations and personal radio devices. Direct FM transmitters use a more complex process to achieve frequency modulation. Instead of modulating the oscillator directly, the audio signal first modulates a lower frequency oscillator. The resulting signal is then multiplied and shifted to the desired broadcast frequency. This method allows for greater stability and precision, making it suitable for high-quality FM broadcasting where signal integrity is crucial. In comparing direct and indirect FM transmitters, the key differences are in complexity and performance. Direct FM transmitters are simpler and easier to implement, while indirect FM transmitters offer better frequency stability and are preferred for professional broadcasting. The choice between the two depends on the specific requirements of the radio station or application. Now that we've covered transmitters, let's shift our focus to radio receivers. Receivers are devices that capture radio signals from the air and convert them back into audio or data. The most common and advanced type of receiver is the superheterodyne receiver, which we'll discuss in detail. Understanding receivers is essential for grasping the complete picture of radio communication. Superheterodyne receiver is a revolutionary design that has become the standard in radio technology. It works by converting incoming radio signals to fixed intermediate frequency, IF, which is easier to process and filter. This approach greatly improves selectivity and sensitivity, allowing for clearer reception even in crowded radio environments. Let's break down the key components that make this possible. RF amplifier is the first stage in a superheterodyne receiver. Its job is to amplify weak radio frequency signals picked up by the antenna, making them strong enough for further processing. By boosting the signal early, the RF amplifier helps improve the overall sensitivity of the receiver, ensuring that even distant or faint stations can be heard clearly. Mixer is a critical component in the superheterodyne receiver. It combines the amplified radio frequency signal with a signal from the local oscillator. This process produces new signals at the sum and difference of the two frequencies. The difference frequency, known as the intermediate frequency IF, is selected for further processing. This conversion is key to the receiver's ability to tune and filter signals effectively. After mixing, the intermediate frequency IF amplifier takes over. It amplifies the IF signal, which is now at a fixed frequency, making it easier to filter and process. The if amplifier is crucial for improving selectivity, allowing the receiver to isolate the desired station from others nearby. This stage is a major reason why superheterodyne receivers perform so well in crowded radio bands. Local oscillator is an essential part of the superheterodyne receiver. It generates a stable frequency that mixes with the incoming radio signal in the mixer. By adjusting the oscillator's frequency, the receiver can tune to different stations. The local oscillator's precision directly affects the receiver's ability to select and process the correct signal. Tracking refers to the coordination between the local oscillator and the RF amplifier as the receiver is tuned across different frequencies. Proper tracking ensures that the receiver maintains optimal sensitivity and selectivity throughout the tuning range. This is achieved by carefully designing the circuits so that both the oscillator and amplifier stay in sync as you change stations. Image frequency rejection is a vital feature in superheterodyne receivers. When mixing signals, unwanted frequencies called image frequencies can also be produced. If not properly filtered, these can cause interference and degrade reception quality. Image frequency rejection involves using filters and circuit design techniques to block these unwanted signals, ensuring clear and accurate reception. Typical superheterodyne receiver consists of several stages: antenna, RF amplifier, mixer, local oscillator, if amplifier, detector, and audio amplifier. Each stage plays a specific role in processing the radio signal from reception to output. Understanding this block diagram helps visualize how the signal flows and is transformed at each step. The antenna is the entry point for radio signals. It captures electromagnetic waves from the air and converts them into electrical signals. The quality and design of the antenna greatly influence the receiver's ability to pick up distant or weak stations. A well-designed antenna is the foundation of effective radio reception. The detector, or demodulator, extracts the audio signal from the intermediate frequency. This stage is where the actual information, such as music or speech, is separated from the carrier wave. The quality of the detector affects the clarity and fidelity of the final audio output. The audio amplifier boosts the extracted audio signal to a level suitable for driving speakers or headphones. This final stage ensures that the sound is loud and clear enough for listeners to enjoy. The design of the audio amplifier can influence the overall sound quality and power output of the receiver. Selectivity refers to a receiver's ability to isolate a specific station from others nearby in frequency. High selectivity is achieved through careful filtering at the IF stage and precise tuning. This feature is especially important in urban areas where many stations broadcast close together. Sensitivity measures how well a receiver can detect weak signals. It depends on the quality of the RF amplifier and the overall design. High sensitivity allows listeners to pick up distant or low-power stations, expanding the range of available broadcasts. Noise and interference are common challenges in radio reception. They can come from electrical devices, atmospheric conditions, or other radio stations. Good receiver design, including proper filtering and shielding, helps minimize these issues and ensures clear audio output. Automatic gain control, or AGC, is a feature that automatically adjusts the receiver's gain to maintain a consistent audio level. This prevents sudden changes in volume when switching between strong and weak stations. AGC improves listening comfort and protects speakers from damage. Some advanced superheterodyne receivers use double conversion, where the incoming signal is converted to two different intermediate frequencies. This technique further improves selectivity and image frequency rejection, making it ideal for professional and high-performance radio equipment. Crystal filters are often used in the IF stage to achieve extremely sharp filtering. These filters use the properties of quartz crystals to allow only a narrow band of frequencies to pass, greatly enhancing selectivity and reducing interference from nearby stations. Squelch Control is a feature that mutes the receiver's output when no strong signal is present. This prevents annoying background noise when tuning between stations or during periods of weak reception. Squelch is especially useful in two-way radios and communication receivers. Demodulation is the process of extracting the original audio or data from the modulated carrier wave. Different techniques are used for AM and FM signals, each with its own advantages. Understanding demodulation is key to appreciating how receivers turn radio waves into sound. In AM receivers, demodulation is typically performed using a diode detector. The diode rectifies the signal, allowing only one half of the waveform to pass. This process recovers the audio information from the amplitude variations of the carrier wave, making it audible through speakers. FM demodulation is more complex than AM. Common methods include the use of a discriminator or phase-locked loop (PLL). These circuits detect changes in frequency rather than amplitude, allowing for high-fidelity audio with excellent noise rejection. Tuning mechanisms in receivers allow users to select different stations. This is achieved by adjusting the local oscillator and RF circuits to match the desired frequency. Modern receivers often use digital tuning for greater accuracy and convenience. Digital radio receivers represent the latest evolution in radio technology. They convert incoming analog signals to digital form for processing, offering improved sound quality, additional features, and better resistance to interference. Digital receivers are becoming increasingly popular in modern communication systems. Software-defined radio, or SDR, uses software to perform many of the functions traditionally handled by hardware circuits. This approach allows for greater flexibility, as the same receiver can be reprogrammed to handle different types of signals and standards. SDR is widely used in research, military, and advanced communication systems. Radio transmitters are used in a wide range of applications, from broadcasting music and news to enabling two-way communication in emergency services. They are also essential in aviation, maritime, and military operations, where reliable wireless communication is critical. Radio receivers are found in everyday devices like car radios, smartphones, and emergency alert systems. They play a crucial role in keeping people informed and connected, especially during natural disasters or important public announcements. In emergencies, radio transmitters and receivers provide a lifeline for communication when other systems fail. Battery-powered radios and portable transmitters ensure that vital information can be shared even during power outages or network disruptions. Radio remains a popular medium for entertainment, offering music, talk shows, and live events. Its ability to reach wide audiences and provide real-time content makes it a unique and enduring form of media. Educational radio programs have been used for decades to reach students in remote areas. Radio's accessibility and low cost make it an effective tool for distance learning and public education campaigns. Scientists use radio transmitters and receivers in fields like astronomy, meteorology, and wildlife tracking. Radio technology enables the collection and transmission of data from remote locations, supporting important research and discoveries. Navigation systems, such as those used in ships and aircraft, rely on radio signals for accurate positioning and communication. Radio beacons and transponders help guide vehicles safely to their destinations, even in challenging conditions. The future of radio technology is bright, with ongoing advancements in digital processing, miniaturization, and integration with other communication systems. As technology evolves, radio will continue to play a vital role in connecting people and sharing information worldwide. In this video, we've explored the core components and principles of radio transmitters and receivers. From AM and FM transmission methods to the intricacies of superheterodyne receivers, each element plays a crucial role in making radio communication possible. Understanding these concepts provides a solid foundation for further study or practical application in the field. Thank you for joining us on this journey through the world of radio transmitters and receivers. We hope this overview has clarified how these technologies work and their importance in modern communication. Stay tuned for more in-depth videos on related topics, where we'll dive even deeper into the science and engineering behind radio systems.